So we can start. Thanks a lot for attending this session. The title of the talk is Managing Telco Infrastructure and Applications at Scale, an Open Source Approach. My name is Kashif Khan. I will briefly give you an overview of what I'm going to talk about in this next 30 minutes. So historically, telco infrastructure was designed to be vertically integrated, as we all know. You could just brought specialized hardware and then run vendor-specific software and rely on expensive lifecycle contracts. That model worked when innovation cycles were pretty slow, but today it's kind of unsustainable, as we have seen. And cloud-native technology has changed these expectations. We have declarative APIs, continuous delivery, elastic scaling, and whatnot. So my goal in this talk is to show how we can manage the telco infrastructure the same way we manage the applications, using open source, Kubernetes native tooling, and automation at scale. So the first few slides in this talk, I want to discuss about the telco challenge and how we are going to solve it. But in the latter part, I'm going to do a deep dive into an open source project called MetalCube, which provisions or allows you to provision your Kubernetes cluster on top of bare metal servers. So a few words about myself. I wear a couple of hats. I am one of the maintainers of a project called metalcube.io, which provides, as I said, Kubernetes native API for bare metal provisioning. I'm also a co-chair for the CNCF Technical Advisory Group for infrastructure, which means that I am spending a good amount of time looking at how infrastructure automation is evolving across the industry. And I also work as an open source architect for Ericsson software technology in Finland, where we are actively driving this transformation in the telco space. So what I will share today is also coming from the experiences of building, operating, and scaling these systems, not just from theory. So let's talk about the telco journey. I think most of you might be already familiar with this picture, but I just wanted to bring this back into the context. As we know that initially what we know as telco was actually a rack of proprietary boxes, and each running a single function with like completely siloed applications. Then we gradually moved towards the network function virtualization. We were using the virtualized stack. This gave us some agility, but then again, there was quite a lot of manual integration that were needed. And of course, when it comes to resource efficiency, we were still not there. We briefly saw also the disaggregated part where the control plane and the user planes were actually disaggregated, and it was then back again running on the VM itself. Eventually, then we went to cloud native or CNF or the containerized network functions running in Kubernetes, managed declaratively and designed for elasticity. And all of those telco applications are mostly running on CNFs. So this journey is about the abstraction from siloed hardwares to VMs, and then from VMs to the containers. Each step has improved the resource utilization, the agility. But telcos are unique. They require, of course, not only running things on containers, but there are always these famous five nines that we talk about: availability, deterministic performance, and of course, global distribution. That's actually what makes this whole journey quite a lot of challenging. So, as this picture shows you, unlike a single enterprise data center, telco networks actually span across hundreds or even thousands of sites, central data centers, regional aggregation hubs, and even far edge locations. There are also, this is not a full picture, there are also deep edge, for example, which we can include here. So the challenges that we are talking about here, first of all, is scale when it comes to provisioning servers and running these applications, thousands of microservices across this whole whole span. Provisioning is a challenge automatically. If these are not automatic, then of course we have a lot of challenge to face. Then comes not only the provisioning, but also the lifecycle management of these. If we know that hardware fails, NICs can die, firmwares become outdated. So these must be handled programmatically and automatically. Then there is, of course, the zero downtime issue. You can't just take down any telco core during an upgrade. For example, you need to have HS strategies. It must be built in at both infrastructure as well as the application layer. Then you have security and compliance, of course. Telcos are highly regulated, as we all know. So everything from data sovereignty to, for example, lawful intercept, we need to also respect each of it. And then finally, and most importantly, as we have moved, as we saw in the previous picture, we have moved from an integrated silo towards a cloud-native architecture. And what essentially that has allowed us to do is also to run these applications on commercial off-the-shelf hardware. But when it comes to commercial off-the-shelf hardware, there is, of course, these multi-vendor platforms, and we don't want to also get like a vendor lock, for example. So all of these challenges are actually driving us more towards going cloud-native open source approach. And what does actually cloud-native telco look like? I have just given a very simplified approach that we are following. The philosophy, as I said again, treat infrastructure like applications. That means infrastructure is declared in YAML, reconciled by controllers, and also self-healing when something bad happens or when there is some drift going away. So you can ask that why there is still virtualization and we are running both in this world. Of course, there are still some deployments which are like transitioning from like running on VNFs towards becoming to or running towards CNFs. So for that, this is time being, we still allow to have this virtualization layer. But what's more interesting in this picture is the unified infrastructure management. So when it comes to the application deployment, you don't need to worry about where your application is running. It's mainly this infrastructure management layer which takes care of running your containerized network functions or CNF on top of the deployment. I'm actually not here to advertise anything about Ericsson itself, but I just wanted to show this slide for the context. So we in Ericsson, we have this Ericsson Cloud Container Distribution, or CCD as we call it. It is distribution with full compliance with CNCF. And we always have upstream first design, and it just gives you a small picture of the open source tool that we are leveraging. But for this talk, I am mainly interested to look a bit deep down into this LCM stack on the Cluster API, and mainly, as I said in the beginning, I'll be talking mostly on the Metal Cube side as well. So this is, again, the simplified architecture from a couple of slides back. Now I am more in, deep, diving into what are the projects that we are utilizing for the architecture. We use, of course, Kubernetes, just not for workloads, but also for infrastructure lifecycle. This is where these projects like Cluster API and metalcube.io comes into play, giving us Kubernetes native APIs for servers, clusters, as well as for control planes. Just wanted to ask how many of you have previously heard about Cluster API or MetalCube, for example? Right, I think fair enough percentage. I would say half of you already know. So, and then probably for the other half, I will give a brief introduction of what Cluster API is as well. Well, anyhow, the goal in this architecture is to manage, as I said, a bare metal telco site the same way you would spin up a cluster in a public cloud, for example, EKS or GKE cluster, apply a manifest and let the automation do the work. So this is a simplified bare metal stack, and it is coming from the metalcube.io. So it's a very high-level overview. At the bottom, you have the infrastructure, or let's say bare metal servers that we want to manage using the Kubernetes native API. On top of that, we have the metalcube components. First comes the bare metal operator, which actually reconciles an object which is called bare metal host. And bare metal host is actually the API which represents the server inside the Kubernetes world. And the bare metal operator is talking to that server or the bare metal host using OpenStack's Ironic. It can install operating system, it can configure BMCs, for example, attach storage, set up networking, and do everything that you would want to do on your bare metal servers. And above that, there is a plugin to Cluster API. Metalcube has a provider for Cluster API, and that is the CAPI provider Metalcube. CAPI is actually a short form of Cluster API, which I'm going to introduce in the next few slides. And of course, at the top, workload would run on top of Kubernetes cluster once you have provisioned this bare metal server with the correct configuration. So let's zoom into a cluster API. So cluster API is a SIG cluster lifecycle project. It manages the lifecycle of clusters declaratively. You can create a cluster object and controllers make it real. What's more powerful in the provider model, so that is denoted by this dash infrastructure. This can have many different infrastructures as you wish. Currently, there is a big list of providers that Cluster API supports. As an example, there is a provider for GCP, and there is a provider for AWS, there is a provider for Azure, VMware, OpenStack, you name it. But for our case, or when Metalcube, we also have a provider called Metalcube, as you saw in the previous picture. And same declarative model works across different environments. So this is really powerful in a sense that you can treat your edge site just like a cloud region. A management cluster spins up and manages the target cluster at scale. And of course, it has a bunch of other very useful features, like it supports failure domains that are, of course, crucial for telcos. You don't want all your replicas in one rack or one power domain, for example. You need topology awareness on rack level, on regional level. So also, if you think about upgrades, for example, Cluster API and Metalcube combinedly can orchestrate, for example, rolling updates across nodes, minimizing the downtime while respecting the, let's say, HA policy. So this is really crucial in carrier-grade environment. So at this moment, I would like to probably just drop my Ericsson hat and maybe talk about a bit more about the Metalcube. So I don't have the hat, so I'll just drop my Ericsson hoodie. And I have a cool Metalcube shirt. So yeah, mostly, as I said in the initial slide, I am also a maintainer of this project. It was a sandbox, CNCF sandbox project until early last week. We have been promoted to become a CNCF incubating project. The announcement is not yet done, but the plan is to actually announce it along with the Kubernetes release, which is upcoming on Wednesday, I guess. But anyhow, it just this moment. Excuse me, I'll just take a few seconds to drink some water. So it's the incubating project, as I told, and it provides. Also, I have told that it provides Kubernetes a native API for bare metal provisioning. It's self-hosted, it's self-managed, which means that once you bootstrap your cluster on top of bare metal, it can manage its own infrastructure. For telcos, bare metal, you might ask why actually we are going bare metal way. And the answer is that for telco, bare metal is kind of non-negotiable in a sense that cloud VMs can't always give you or meet the deterministic latency, those 5 nines that I was actually talking about in the beginning, or even the throughput, for example. And running the 5G core functions, application RAN workloads often require direct access to your hardware, and even on the nowadays the accelerators, and of course optimization on the hardware level in much more necessary in that sense. And this is where MetalCube actually comes. It bridges the gap, and it gives you the cloud-like experience while you are still running your workloads on top of physical server. So the whole idea is actually you have a bunch of physical servers, and then you want to deploy a Kubernetes cluster on top of your physical server. But as I have told you, that we also have an API to represent these physical servers inside Kubernetes. This API is, or this custom resource that we are deploying to represent a server is called bare metal host. And bare metal host is reconciled by a controller called bare metal operator, which I probably showed you, and you might have remembered it from the telco, from the bare metal stack picture. But anyhow, what information would you actually give that I will probably explain a bit later, but let's assume or let's see what is really the workflow for the Cluster API provider MetalCube in this case. So the idea, as I said, was to provision a bare metal server that is on the right corner, have a Kubernetes cluster on top of it. To do that, Cluster API actually first initializes an object called machine. The idea is that this machine, which represent node of Kubernetes, which can be a control plane and a worker. And this machine, as I have actually also showed you, can be deployed on top of multiple different providers, AWS, Azure, or now we are talking about mostly MetalCube. And the MetalCube, in the MetalCube machine, we have already now told that, okay, the infrastructure would be like a would be a bare metal server. But then when it comes to what details do I need to give for that bare metal server, I am giving those details in a custom resource called bare metal host. And this operator that is sitting in between MetalCube machine and bare metal host is bare metal controller. And once you have actually provisioned or given enough information to provision this bare metal server, the information could be what images do you want to provision on this server, what is the version of the Kubernetes, for example, that you want to deploy on top of it. After giving all of these informations, the reconciliation would actually provision a Kubernetes cluster on top of the bare metal server, and it is the same representation through all these machine, MetalCube machine and bare metal host. So if you notice the symmetry, everything here is actually expressed as Kubernetes objects, whether it's a bare metal host, a machine, or even a cluster. The same reconciliation model applies at every layer. And this is where I was mentioning that the information that you would need to give are like the baseboard management controller, or we call it the BMC credentials, and the BMC address, and let's say the host MAC address. If you provide this information, from that point onwards, the bare metal operator is able to power your host on, mount an image, run PXE, IPXE booting, for example, and install the operating system. So just like quick overview of how it's doing. So this is the Kubernetes world we have, where you have given the necessary secrets, and then you have told the other specs that are needed for bare metal host to get provision your server. And then you have also given the BMC addresses so that the standalone Ironic can sit in between and now help a bare metal operator to provision your Kubernetes cluster. We have component which we call Ironic Python agent, which is in this picture is depicted as the deploy RAM disk. The task of this Python agent is that when you do the PXE booting, for example, it boots up your server. It does operation also called inspection. It inspects your hardware and then gives back this information in the Kubernetes world as and it is reflected back in the bare metal host's status. And what it does one more important task, that is also to copy this OS that you would like to provision on top of bare metal host, so that once you boot up again next time, you are now booting up from the disk using the host you wanted. I wanted to show a small demo on how actually we are doing it. So let me first, it's a pre-recorded demo because of course it takes quite a lot of time to provision an OS and also the cluster itself. So we have on the top left, we have already deployed 2 bare metal hosts, as you can see, node 0 and node 1. Both of them are in available state, and by available state means that they are now ready to get provisioned. They have been inspected, we know the hardware details, but they have not been provisioned yet with any host OS, for example. And you might ask why I am showing Vish, because even when I am talking about bare metal hosts, for us, we have actually developed a development environment called Metal Cube Dev, where we are testing all of these things. So we actually deploy or make these provisioning on top of VMs, but we are not using Vish commands. We have a tool called Virtual BMC, which we use to actually do or just act the similar way that you would be doing when you are provisioning a bare metal host. So you are talking through the VMC, not using the Vish commands, and hence I'm just showing you that using a script, whenever I am turning on and turning off a server, I am not using any Vish commands, for example. We are just using those kubectl patch commands, as you see in the functions for stop and start. And I am just changing the online in the spec of bare metal host from, is it like true and false? And you can also see the same. So currently the VMs are in running state and the online state is true. Let's start the demo. Let's see what we do here. It's just giving you the whole picture. There is also a provision function, but we will use that a bit later. So we first say that, hey, please stop. And then it has patched, and you would see that the change in the online spec has become to false. It will take a bit of time for VBMC, but now you can see that the VBMC had make sure that the VMs are actually shut off. And same goes for start. The online status just changes from false to true, and then you will see that it will start to boot off. And here we are showing the serial logs just to show that when it's booting on, what kind of things are running. And if you remember from a couple of slides back, this thing that is running now here is called the ironic Python agent, or the RAM disk. So this is just to show you that how we are controlling this like bare metal inside Kubernetes world using just the Kubernetes native API. And if we do the same a few slides back, okay, so this is, sorry to actually run it too fast because I think I don't have enough time, but I just wanted to cover all of this. This is a representation of a bare metal host again, and you can see a lot of information is there, when it was provisioned, what are the changes that we have done, but most importantly also the hardware details that it has inspected from using IPA, for example. So now there is currently no cluster, and let's try to provision a cluster on top of one of those servers. This script, what it does is that it provisions a cluster and makes one of these bare metal hosts as a Kubernetes control plane. And you would see that the serial logs would also actually show you that what is really happening. The whole operation, what it does is that that IPA that was running a while ago, it now copies the image that I have told here to provision on top of this bare metal host, and then boot up with that image. And that image also contains the cloud in it, which actually is necessary for making this bare metal host as one of the control planes of a Kubernetes cluster. And you can see that the state has changed to provisioning. It has started working. And then after a while, it would actually change to provision state. Let me go a bit fast here. So now it has actually provisioned. And this is simply the operation that I wanted you to understand, that how it is kind of in some sense pretty flexible to you to actually operate the lifecycle of your bare metal server inside the Kubernetes world. Okay, I think then I will again bring back the picture just to discuss about what I have actually now gone through in the last 20 or 25 minutes. So you have seen that again this picture where we are now currently going cloud native, but I guess you guys have had an idea now why we are also using bare metals to actually deploy this Kubernetes cluster and also the CNFs on top of that. This is why the idea is that the telco operators want agility, scale, and automation. But with this kind of reliability that is required, bare metal provisioning through Kubernetes actually closes a lot of these gaps. For edge deployments, for example, this is even more critical. Imagine deployments or deploying hundreds of microservices at remote sites, for example. You can't ship, for example, humans everywhere to plug in a USB stick, for example. You need fully automated declarative provisioning. And that's the foundation of cloud native telco. So to wrap up with the key points, of course, provisioning at scale is hard. You must design failure domains, racks, data centers, different sites. You have to expect hardware failures, but you have to build automation to tolerate those failures. You have to have also zero downtime upgrades, for example. Those are in many cases mandatory. We are not saying that we are still there, but of course there would be a time when we would be also be able to provide these sort of mandatory features. Then, for example, breaking down these monoliths into microservices, that will pay off. That pays. We have already seen that pays off. CNFs are already proving more resilient and easier to scale than VNFs that we have seen. And moving away from the proprietary stacks to open source is, of course, inevitable. It reduces, as I said, vendor lock and accelerates innovation. But it also means that telcos must grow internal cloud native expertise. And I think the road ahead would be to optimize your performance. There are things like accelerators in Kubernetes, tighter integration with those accelerators in Kubernetes, for example, and ensuring compliance. But the foundation is telco will be managed declaratively, at scale, and through open source.